Everyone, how we doing? Today, I kind of wanted to talk about a little bit of I think a touchy topic when it comes to engines, especially two strokes, and that is emissions. We hear this term all the time be applied to uh, vehicles, small engines, lawn tools, factories, manufacturing, everything. In this specific context, I'm going to be talking about it. I'm just going to be talking about uh, two-stroke engines. And the reason I have this one is because this is the one that I've made into my kind of model as I've learned these engines. This is kind of just like an instructional tool that I have videos on, or I'm going to have videos on, basically just kind of diagramming a lot of the core parts of the engine. And so I cut an engine in half, this two-stroke, and it just allows me to visualize what's happening, and also hopefully just as helpful to other people as they kind of approach this topic of learning two strokes and really just need a three-dimensional model that they can just quickly identify and see parts, what they're called, everything like that. Because sometimes like a lot of it is just like, what is this called? Like, what is this part called? Then you have to like search like, what is the part on two stroke that does that, or does this, or connects to that, or whatever it is. You just need a 3D model. You can pull a picture online, everything. I know, obviously, but like just having something physical is just super helpful. Especially if you're a visual person like me, you can just quickly see, okay, here's what's happening as the piston moves down and the exhaust port opens up. Are the transfers open yet? When does the intake port open up? What happens with this, with that, and everything like that. One specific aspect of it that I want to talk about, and again back to emissions as it relates to two strokes, is the problem of short circuiting. Short circuiting is basically the small window of time that occurs when you're not going to be able to see this too close, but basically when your exhaust port is open as well as your transfers. So in this engine, this is a loop scavenged two-stroke. You can see it has your two transfers right there, intake port and exhaust port. So right here is right where the blowdown process starts. And we go some more degrees down, we have the end of the blowdown. And that blowdown is the window of time or number of degrees which your piston is moving down and your exhaust port is open. Blowdown stops right when the transfers occur. So blowdown is a window of time that your exhaust port is open to right when the transfer is open for this particular two-stroke setup. There's a lot of different two-stroke setups, but for this one, that's how it works. And the problem with this is that after the blowdown happens, your transfer is open. Your transfers are going to be moving fresh mixture from the bottom crankcase up to the cylinder, and this fresh mixture is not burned yet, and it's going to be mixing in with some of the old exhaust, still trying to escape. And because of that, you have a high pressure system and a low pressure system, and the pressure is going to be escaping, pushing the new mixture out. And unfortunately, you lose a lot of efficiency out of the engine that way, and you lose a lot of fresh mixture right out to the atmosphere. This creates a problem of particulate matter, basically just completely unburned mixture escaping into the atmosphere or the environment. And unfortunately, that is CO2. And carbon deposits, they hear particulate matter. It's like this toxic kind of basically carbon deposits that escape and things like that are toxic to breathe and to humans, as well as the atmosphere. The problem is kind of an innate design problem with these engines. There's not really a way you can avoid the exhaust port being open and not have the transfers open too, because if you have the exhaust port open, you have to, your exhaust port would have to close, then your transfers would have to open, and then it would fill the top. The problem, this is like the great design problem that these engines have, is what's the percentage basically allowance of that, because you can't restrict them completely. Your pressure would be so out of whack, you wouldn't have consistent fluidity of the closed system. It's like, if you look at charts of this, I mean, this is a calculated issue for the past 50 years. I mean, or further, as far as thermodynamic study of this has been happening. I mean, you have, every manufacturer will have a different, allowable percentage for escaped fresh mixture out the exhaust, because they have to, one has to be open when the other is open. They're not completely mutually exclusive. Now, there's some things that you can do to kind of alleviate that. So scavenging is basically the term that applies to the replenishing of new mixture into the system, pretty much. As old mixture goes out, new mixture comes in. Now, I'm referring mixture is a mixture of, your oxygen and gas, your air and fuel mixture, right? It's a specific ratio that has to exist to produce proper and healthy combustion. And the issue is that you have a process where that has to be replenished. And so you can get a loop scavenged engine, which this is, basically means that as your crankshaft is spinning like this, it'll be moving air kind of in a loop pattern, right? As it goes up the transfers, it kind of retains that loop a little bit, and ideally it would loop around and kind of go out the exhaust. And the exhaust ports are usually shaped in such a way that it maintains back pressure, because you don't want a huge exhaust like this, and then to escape, because it would just create this uneven pressure. It's all about, that's really the battle we're facing, is all about pressure. Because if you go to different elevations in the world, your pressure is going to be different. So they kind of create this stuff usually at a sea level kind of pressure, where the pressure is a little more normalized. If you're high on a mountain, your pressure is going to drop, and so your engine's actually going to function a little differently. So it's like there's so many variables and factors to get this ratio correct. Your pressure has to be such that your replenishment is still healthy, and that you don't create so much backup, basically. Because what happens if there might be too much backup is you may begin to go the other way, back into the carburetor. So you may develop spitting of mixture back out the carburetor, which you don't want. Some manufacturers have developed kind of like a reed valve system to kind of prevent that backward motion happening. Some two-strokes don't have it. Like, this does not use any reed valves. This just, again, you're probably not going to see that in a traditional kind of loop scavenge engine. But that's one way. There's other manufacturers have created a valve system with like poppet valves. Other ones have tried to mess with the spark plug location. There's been studies that people have actually created multiple spark plug two-strokes to provide a fuller combustion for the mixture on top, to reduce the amount of fresh mixture lost. Because if the more you just burned, okay, you're not gonna, the less, I'm trying to figure out, if you have a more complete burn cycle, you're not going to have kind of the residual explosions, if you will. Meaning, if you have one spark plug and it's poorly positioned, you're only going to burn that really spot of the mixture. Then you have all this kind of still pseudo unburned mixture left, and then you have fresh air that blends with that. Then you have so much lost into the atmosphere. So that will lead to a higher amount of emissions. If you have multiple spark plugs, it's a more complete burn. Then you have less fresh mixture directly going out into the atmosphere. I've there was a study in I think it was India. They published a research paper where they actually got up to 3 spark plugs, and that was the most that performed the best in terms of emissions of the overall emissions of the engine, as well as actually did well on performance too. Which is why I want to build a multiple spark plug engine, is to just test out how it performed and how it did. And I did that, and it's sitting over there. And you can go watch that content if you want. I haven't yet built the CO2 monitor to gauge to see what the number is. I'm really curious to see what that total output is. But anyway, so that's kind of it's this balancing act of what do we do with the pressure? What do we do with the the overall mixture? How much mixture do we want it? More lean, more rich? Obviously, if we make it a little more lean, it's overall better on the emissions. But if it's more lean, we're having more. We're going to have more air. We might have more pressure. So it's just it's such a calculated cost, right? It's the teams of engineers have decided upon these specific ratios for fuel, air, back pressure. I mean, overall size of the cylinder, what size of piston, do we need 1 or 2 piston rings? I mean, there's so many factors go into this. What's the shape of the exhaust? Is it a cone? Are we going to make it flat? What's the shape of the intake? And it's incredibly complicated, but it's all kind of a band-aid around the problem that happens with short circuiting. You can't eliminate short circuiting 100%. It's just you would have to completely redesign your thinking in terms of these engines. You can't escape the problem, and the problem and because of that, we're left in this spot in the world where it's like, okay, we have these engines that perform at such a way. They're very powerful, and they make the most power for their size out of any engine ever made, but they make the worst emissions out of any engine ever made. There's a statistic that if you drive a car, a modern fuel-injected car, 900 miles, that's the emissions equivalent of a 2-stroke lawn tool running for an hour. So when people say, do lawn tools really matter? Do all this matter? Does it really, it's such a small engine? Unfortunately, it really does. And I think that's the unfortunate truth that we're faced with in the world is we've engineered ourselves into this spot where we have this really powerful motor that allows us to do so many things in the world, but it's highly inefficient, and it loses 40% of its efficiency, and it pollutes so much. And it's like but it's such an interesting design problem, because on paper short circuiting can't be eliminated, but I don't know if we've explored all the possibilities. Like, I think it's still truthfully an open problem that somebody, if they really put their heads down and try to think through the design and engineering of these engines, I think we could get to a spot. The problem is money, time and money and investment. Big companies unfortunately went under because of the emission regulations that were put in place, and they couldn't keep up. Like McCulloch chainsaws, they went out because of emissions regulations. And companies are looking at the investment needed to completely redesign their engines, and they can't spend millions and millions of dollars to do that. So they're having to just put these band-aid solutions over the problem, or they're switching to 4-strokes, which aren't as bad as emissions, but still pollute. But it's like an open problem that needs a lot of time and money thrown at it, and nobody really has the resources to. I don't want to say nobody has resources to do that, but it's like a cost benefit, right? These big companies are looking at the problem of like, well, if we invest $20 million with a team of engineers to redesign our two strokes completely and make them reduce emissions by 20%, whatever, what's the perceived benefit in terms of money for the company, right? That's what they're asking, and it's pretty low, and it's going to lead to increased costs for the consumer. So you and me buying a weed whacker, it might be double the price. Hold on, I'm gonna check my phone. It's still recording. I think a low battery. All right, I think we should be good. It's like 10%. So if it switches off, you know what happened. Companies are left with, well, what do we do? Do we just, we would have to raise the price of the engine just because the amount of engineering time that we put into it, the amount of design and all these people that we have to hire and everything. And that's the problem. And because most two-stroke manufacturers are these huge companies that have the time and resources to do that, that's what we're left with. And most manufacturers are not located in the United States. So there's that factor too of like, a lot of the design is not happening here. It's kind of, it's happening elsewhere. So how do we convince other people in the company in another country to invest the time, money, resources when they're looking at it in their country that doesn't maybe have such stringent emissions regulations? And it's such a big problem, but it's an open problem. It's really is. It just needs people to study it and create 3D modeling, run software that runs thermodynamic analysis of what's happening as the mixture is coming in. If we adjust this angle a bit, move it out. What's happening. That's what it's going to take. But that software, unless you get an open source one and can perfectly calibrate it to what you're trying to do with your engine specs, it's just, it's going to take a lot of work. And especially now that we have kind of the electric motor, market encroaching upon this market here. Like you have electric lawn tools, electric lawnmowers, electric vehicles. The incentive, I fear, to kind of go back to the drawing board of these engines is kind of diminishing very quickly. And I think it's going to reduce down to more of a hobbyist problem, if you know what I mean. I don't think large manufacturers are really going to go back and invest that, just because there's probably not going to be much payoff for that for them in terms of money. The uncomfortable truth with emissions is that it's a problem, but we've kind of engineered ourselves into this hole, and we see with climate change happening, that adds another element. Do we just make the jump to shift focus to electric and then make that at a reasonable, sustainable price, or do we continue working the problem of these engines? And that's kind of what we're left with, right? That's kind of what we're left with. But I think it can be studied, thought of, and figured out by people if they're really interested in it. Especially the spark plug avenue. The spark plug, multiple spark plugs, I think poses one of the more cost-effective ways to drastically reduce emissions the quickest with minimal change. I say minimal because it's really not hard to implement. You would have to change a little bit the design and shape of your cylinder, but after that, it's more of a carburetor tune than anything. And when I say design and shape, you probably would just need to offset one spark plug and then put the other one offset. It's honestly not that, it wouldn't be, in my mind, that's not the hardest thing to do. And also another area that we've seen actually in the automotive space with some companies that actually have tried to do this is water injection methods. Water injection also poses a pretty promising return on emissions too. Water injection methods like post carburetor, direct kind of into the air intake, I think could be a potential solution. that would take a little bit more fine tuning for sure. There would have to be some kind of valve you would have to engineer, or some kind of control to trickle that water down at a consistent rate with what the carburetor is delivering mixture. Those are two quickest options I see. Third option would be a technological advancement with software. We need to create basically a computer system that can plug into these engines, have the necessary sensors that then sends information up to a system that you could control and calibrate remotely. This would be different from vehicles because it wouldn't be embedded. Really, I would like it to be a little more cloud-based. That's a third potential solution that could be explored. But obviously, again, it's time and money. But if someone wants to do that, I think it could be promising. Those are the least obtrusive ways, I think, to go about this problem. A very obtrusive way to go about this problem is to completely rethink how we're doing transfers. I think that there's been a lot of solutions brought over the years and a lot of interesting design decisions. And I think that could keep going to reduce down the total number of emissions possible. And I think that you would really have to study this content in depth and figure out a solution. But that's kind of where we're at. I mean, it's an open problem, right? We see companies what they try to do, but honestly, if it just enough individuals, I think, come together and try to figure this out, I think we get in a better spot, and hopefully get us in a spot where we make sustainability of engines a little healthier, moving in the future, where it's like we don't just have a stark, you can't sell two strokes, you have to move to electric, because I think there has to be a transition, right? There has to be some kind of leveling point, right? We recognize the fact that we're the over excess of CO2 pollution, particulate matter, all these things from engines is a proven fact that is in fact leading to destructive environmental consequences like the human-caused climate change. That's an unavoidable, unfortunate fact. But how do we make that transition off of it the most sustainable for people involved in the industry using these tools? That's really what needs to happen. But again, it takes a lot of time and money, but it doesn't for the individual. And that's kind of where I want to leave it. Because if somebody can figure this problem out, then sell it maybe, or create a prototype and run the numbers, because it's just a problem and it's an open problem. So that's kind of what we're left with. I don't know. Let me know what you guys think. Appreciate you watching. All right. Take it easy.